This is a review of an entire Calculus 2 course. In this review, we will talk about five major topics. So we can start with the first one is the definite and indefinite integrals. So we're going to start with definite and indefinite integrals. And then we're going to go to applications of integrals. So we can talk about applications of integrals. So we're going to talk about several major applications. So especially we can talk about volumes and work problems, and also we can talk about surface area, length. So the subtopics. And then as the third one, we can talk about integration techniques. So there are a lot of integration techniques. So we can talk about that. Integration techniques. And then as under integration techniques, we can talk about all integration by parts, trigonometric integrals, integration substitution, partial fraction method, and all of them. And then the fourth one is the sequence and series. Sequences and series. And then as the final one, we're going to talk about parametric curves and polar coordinates. Parametric curves and polar coordinates. Polar coordinates. Polar coordinates. So these are the kind of topics in a typical Calculus 2 course. So we can start one by one. So let's start with the definite integrals first. So definite integrals. Number one. For reference purpose, I will call 1. So definite integrals. Definite integral. So what's the definite integrals? And we know that we learn about these things. This is just a review. So let's say we have a curve. So we have a curve. Something like that. So let's say it's gonna go between the value A and the value B. So that's in the domain A and B. So so what we normally do is we can divide the domain into equal parts. You know how to divide into equal parts, and why we divide into equal parts? To make the calculation easier. Okay, but in theory, you don't want to, you don't need to do that. Okay, so we divide into equal parts. So let's say you start with the first value, so which is what we normally call the x0 value, that's the first value, and then we have x1, and then we have x2, like that. So we're going to continue that. And then the last one is what we normally call the x nth value. So that means you can divide into n many parts. So then we have x n minus 1, like that. Now what we're gonna do in each interval, and then we assume that they are equal. So what we're gonna do in each interval, we're gonna these intervals are equal size. So the width is the same. So let's say the typical width, they are the same. We normally call delta x, that's the gap of one such interval, and there's a formula for that we know. So how we normally do is, so we call delta x, that's the gap. So delta x is how we get it. It is b minus a, you divide into n many parts. So that's the formula to find the delta x. This delta x sometimes we call h. So sometimes we write this as h. Okay, so we can use that later when we do approximations. Okay, that's one formula. How to find the delta is b minus n. Okay, now what we're gonna do is in each interval, you're gonna pick a sample point. Just pick a point inside the interval. It can be endpoints, it can be something in the middle or somewhere, but it has to be something inside the interval. What we normally call that point is, so let's say, so you pick the first point, the first interval, second point, the second interval. So I'm gonna call that point is, since the second interval, I'm gonna call that point. So that's the point. So just pick a point here. I'm gonna call that point x2 star. Okay, x2 is star because y2 is the second interval. So x2 is star. So that's the point we pick. So we do that like that for each interval. So you pick a point in the interval. Now what we're gonna do, we're gonna find the value at that point. Okay, so we're gonna find the value at the point. So, and you can see you're gonna, because this function you can write as, let's say, y equal fx. That's the function given. That's a graph of the function. Now what we're gonna do, we're gonna evaluate the function at that point. So that's the one. So we're gonna evaluate at that point. Okay. So let's evaluate the function at the point. So we're gonna pick that value as the typical value for the whole interval. So that means for the entire interval, we're gonna pick that as the value. Okay, whatever the value you get at that point, we're gonna consider that as the actual value for the whole interval. So in this case, that's the value. So it's gonna go like that. Okay. So and then what we can do, we're gonna draw the rectangle. So that's what you get for that interval. And then what we can do, we're gonna do the same with other intervals as well. So it's like actually outside. So let's try to put it inside. Good. So that's for the first interval, and we do the same thing with the other intervals as well. So let's pick a point in the other interval. So let's go to the next one. So I'm gonna say that's the point you like. So we can evaluate at the point. So we can evaluate at the point. Yep. And then so that's the value we can consider for the whole interval. That's a representative value, and then that's the rectangle you can for that. Okay, so we're gonna keep doing it for each interval. So pick a point inside the interval and find the area of the rectangle. So what we're gonna do, we're gonna find the area of this rectangle. This is very easy because since we know the function value, so the function value would be, so what's the function value actually? So you can see in this case the function value is, because you evaluate the function at x2, so that means the function value has to be f at the function value, that means x2 star. So that's the value you get, and that's the height of the rectangle. So that means you can simply find the area of the rectangle. So it's going to be delta x, that's the width, times the height, fx2 star. Okay, so you're just going to keep doing that for every interval. So let's do that. So I'm going to draw them. So let's say this is the typical value, so you get, and then you draw the corresponding rectangle. So keep doing it, and then for this one, let's say this is the value you get. So this is a rectangle you get for that, and let's say this is the typical value. So it's up to you what you're gonna pick, and then keep doing it. Okay, so let's say this is the value you pick. So that's what you get for that. So you pick a value inside the interval. That's it. Okay, so that's what you get. And then what you're gonna do now is you're gonna add them. Okay, so you simply add these all the total area. Good. And then you can see that that's an approximation. If you add these all the areas, you can see that that's an approximation to the area below the curve, right? Area below the curve and above the x-axis. So that's an approximation to the area below the curve and above the x-axis. That approximation is what we call the Riemann sum. So what we did was we're going to divide the interval into equal parts. Again, equal to make the calculation easier, so we can say x naught, and then we're gonna go with x1, x2, like that. So xn is the last one. So we divide into parts, and then once you divide into parts, how we divide it? You divide into equal parts. So we call the gap is delta x. Now what we're gonna do? We're gonna calculate the sum. Okay, we're gonna calculate the sum. So you can see that there are n many parts. So you can start 1, 2, up to xn. So you can see there are n many parts. So what we're gonna do? We're gonna add them. We can add all those areas. So there are n many parts. So I going from 1 to n. So one area would be the height is fx. Let's say ith one star. That's the height of a general one, and the gap is delta x. So that's the height and the width. So that's the height and that's the width. Okay, so the height and the width. Now what we're gonna do? We're gonna divide into more and more parts. How you write in mathematics? We write that in, you send n to infinity. So what we're gonna do? We're gonna send the limit. We're gonna send the limit when n goes to infinity, because you can see that when you do that, you're gonna get a function of n. You're gonna get a function of n. Now what we're gonna do? We're gonna divide into more and more and more parts. Okay, more and more and more parts. So then when you do that, what's going to happen? You can see there are errors. Like for example, if you look at the first one, this is underestimate because your actual curve is bigger. And if you look at the last before the last, you can see this is overestimate because there are more outside, so it's overestimate. So what happens is it's kind of cancel each other. So when you divide more and more parts, this error gets smaller and smaller and smaller. When it goes to infinity, what happens in theory, this error becomes 0. So, and once you do that, that limit is what we can do. There's a representation. We can write this as an integral. So we can write this one as starting value a, ending value b. We can write this one as fx dx. So that is a notation. That's a notation, and we call this is the definite integral. So that's a notation. It's a simple notation. So notation is for this area. This area we represent by an integral. Okay. So you know that this sign is the sum. It's a sum. Okay, that is means a sum. So we write it like that. In early days, they write it like that. Okay, because it means a sum. But now we kind of make it stylish and write it like that. Okay, so that means a sum. You add them. You see, you sum up. So that's and called the definite integral. So it's just a sum. So it's a definite integral. So we call this is a definite integral. Why definite? Because we know the numbers a and b. So this is what we call the definite integral. Definite integral. Okay, so and then you can see it's not that difficult. You need to know what are the points that you're going to pick, and then just calculate the sum. And when you send n to infinity, you're going to get a value. That value is what we call the definite integral, and you can see that actually represent the area below the curve. Okay, so that represent the area below the curve. So you can see that. So this definite integral represents area below the curve, below and above the x-axis. Okay, below the curve, above the x-axis, but it's the area below the curve. Area, just to make it easy. Okay, represent area below the curve. That's how we call it, but it means that is below the curve, above the x-axis. A few things that we need to notice, and how to calculate these nodes. These are what we normally call the nodes. How to calculate these nodes? To calculate the nodes, there's a formula for that. So we can calculate the nodes like this. So you can say xi is simply, ith one is simply the first number a times ih, or we can also write this one as a plus I delta x. So that is a formula to calculate the nodes. Okay, not the sample point. Sample point you have to decide. Now let's put them in a node, and also we call this sum is a Riemann sum. So when you write it like that, we call this is the Riemann sum. Okay, it's called a Riemann sum. So So this is the Riemann sum. Good. So one major note is that, so let's write the major note. So you can say that this xi, the sample points xi star, those are the sample points xi star, can be the left end point, can be the left end point, or the right end point, right end point, or the midpoint, okay, midpoint, or any other point, or any other point. Any other point in the interval, so it's ith one, so it's xi minus 1 to xi. It's okay in this interval. So it can be any point like that. So maybe you remember you did things like that before. So let's have a few more things that are important. Now the question is, because this is a limit, what do you know about whether this limit exists or not? Because remember in Calc 1 you talk about limits and there are some limits that doesn't exist. So how do you know whether this limit exists or not? So there's a theory for that. I'm just going to write it. So what it says that it is a theorem actually. So what the theorem says that uh, so the limit exists, okay, limit exists uh, if the function f is continuous. Function is continuous, or it has a finite number of jump discontinuities, or has a finite number of jump discontinuities. Okay, finite number of jump discontinuities. So in that case, it's gonna work. So that's one important thing. So the limit exists if the function is continuous or has finite number of jump discontinuities. In that case, we say the function is okay. In this case, if the limit exists, in this case, we say f is integrable. Okay. So if the function is continuous or has finite number of jump discontinuities, we say it is integrable. Good. Now, so there are a few other things. So there are some positive and negative areas. So positive and negative areas, because we know that the integral represents the area. So let's talk about the positive and negative area. Positive and negative area. Positive and negative area. Doesn't look like in this end. Positive and negative area. So let's look at a situation like this. So let's say you have a graph which start like this, go up, down, up, like that. Now what's going to happen, you can see if you draw the line here, what's going to happen, you get area, but when you evaluate the function to find the Riemann sum, what's going to happen is you get positive heights. So that means this area, you get a positive value for that. But in the same way, if you try to find the area below, you can see that all these heights are negative. So you get negative heights. So that means when you look at the sum, you get negative. And then here you can see it's again, it's get positive. So you can see those values are positive, you get the positive. So that means the area can be positive or negative depending on how the function is. Okay. So it's not always positive. It can be positive or negative. So there are some cancellations going on because you just add them, so it can cancel. So this is the value A and value B. So what now what happen is normally you're gonna draw those rectangles. So when you draw the rectangles, uh, so like that. So those are rectangles, and then same thing here. So you draw you pick sample points and draw rectangles like that, and do the same thing here. And so what happens is, so then you can see you get sigma I going from 1 to n f. You pick some sample points and delta x. So this is a approximation for this area below the curve. We say below, but you can see that's actually what should be bounded by the curve and the x-axis. That's much better because you can see when you say below, it doesn't work for this one. Now what happened when n is larger, you actually get the actual area. So what happened in this case, you get the actual area. Okay, that's what you learn. So what you do now is you're gonna send n to infinity. So and then you simply calculate the area. So you don't have overestimate or underestimate. You exactly get that. Um, so actually, so what should say is algebraic area because the cancellation still works. So if you really need the area, you have to break the integral at those points where it cuts the x-axis, and then take the absolute value and sum it. That's what you have to do, because otherwise what's going to happen is when you try to calculate, it doesn't give you the area. It gives something else because it's going to give the algebraic sum. That's what we normally call. So that means if you say this is the area 1, this is the area 2, this is the area 3, so you can see that 2 is negative. So that means if you integrate from a to b, what's going to happen? A to b is not exactly the area. So it is area a1 minus a2 plus a3 in this case, because a2 is a negative area. So that's what you get. Okay, so that's the kind of basic idea. And then what's gonna do is for the rest of the course is what we are doing is like we try to do this in a different way depending on what kind of integral you get. But we are pretty much doing is just handling this part. Okay, this area. So just as a representation, let's just do one example from this. So let's do this problem. So let's say find the Riemann sum. This is what we call the Riemann sum. So find the Riemann sum. Find the Riemann sum. Find the Riemann sum for fx equal x cubed minus 6x for x going from 0 to 8, 0 to 3 maybe. Yeah. With let's pick some number of points. Let's say n equal 6 maybe, because then you could have points. It's easy. Subinterval n equals 6 subintervals, and taking, because we need to decide what we're gonna pick. So it's not like always obvious. So you pick whatever. So we're gonna do two cases. The first case we're gonna do with the right endpoint, and the next one we're gonna do the left endpoint, right endpoint and the left endpoint. So let's do the right endpoint first. So part A, right endpoint. So so we need a rough graph for that. But when you do the calculation, you really don't need that because you just divide and add them. Because it's telling you what points you need. You're going to pick the right endpoint. Um, So let's look at the graph. So this is x3 minus 6x. So you can see when you plug x equals 0, it's gonna be 0. So I'm gonna do a rough graph for that. Uh, and it's gonna go down and it's gonna go up like that. So that's the kind of rough graph for that. So what we're gonna do is, so when you do the calculation, you really don't need this one. This is just to tell you how it works, but when you do the calculation, you don't need that. So what we can do, let's say divide into 6 parts. Okay, so that means we have 1, we have 2, and we have 3, and then we're gonna divide it again. So those are the points that we can evaluate the function. But what we do is, what they say, pick the right endpoint. So each interval, pick the right endpoint. So that means if you look at the first one, so what's gonna happen is, so you can see this is the right, in the first interval, that's the right endpoint. Okay, so that's the typical value. That means this is what we're gonna get as the representative area. So again, pick the right endpoint in the next interval. That's the right endpoint. So we're gonna pick that value, whatever the value, that's the representative area. Okay, and then same thing, pick the right endpoint. That's the right endpoint. So that's the representative value. Pick the right endpoint. So that's the representative value. You can see there's a huge error here. And pick the right endpoint. So that's the right endpoint for that one. So that's the representative area. Do the same, that's the right endpoint. So pick that. So that's the area we are looking for. That's the Riemann sum. So what we try to do, we try to find this area. So let's do it. So we have delta x. According to the formula, it is b minus a over n. So b is 3, a is 0 divided by 6. So you get half 0.5. Okay, 0.5. So that means each jump is 0.5. So we have 1 and a 2. I just like 2, but we can write the rest. So we can start with x naught, which is 0, and then you're gonna add 0.5 every time. So that means it's gonna be x1 is 0.5, x2 is 1.0, x3 is 1.5, x4 is 2.0, and then x5 is 2.5, and then x6 is 3.0. So those are what we normally call the nodes. So we find the nodes, and we can evaluate the function at the right endpoint every time. Okay, right endpoint. So that means your Riemann sum are 6, yc6, because there are 6 many points. So it is going from 1 to 6. There are 6. So if, okay, you can see that. So what's the first one we can evaluate? We're going to evaluate the first one is x1. That's the first one we can evaluate at x1. And then evaluate at x2, x3, x4, x5, x6. So that means you can write this one as xi. That's exactly what happened. We can start with I going from 1, because we can start with x1. That's exactly match with that, times delta x. So let's plug in that. So that means if we expand this, what happened? The first one is f, the first value is 0.5 times delta x, plus, then the next value is f 1 delta x. So keep adding all of them. The last one is f 3.0 delta x. That's the last one. Okay, now what we can do, we can evaluate the function, because the function is given. So the function is, so what's the function? The function is x cubed minus 6x. So what you want to do is use a calculator and find the values. So you can see delta x is common, so you can take it out. So it is 1/2, and then put the values. So if you calculate at 0.5, you're going to get negative 2.875. Next one would be, if you calculate at 1, you get negative 5. And then if you calculate at 1.5, negative 5.625. So keep doing it. Then you get negative 4. And then you get 0.625. And then you get 9. And if you simplify, you end up getting negative 3.9375. I mean, up to 2 point is enough because this is a rough value, it's not exact value. So it's like roughly 3.9. It's roughly 3.9. Good. So you definitely need a calculator for that. Okay, this is how you calculate the right endpoint. Now let's try to do the same problem using the left endpoint. So if you use the left endpoint, let's see what's going to happen. Do you expect the same answer? Not really, because now you're going to pick the left endpoint. So that means those values are different. Okay, so you will get definitely a different answer. So let's try to do that again with the left endpoint now. So part B, the left endpoint. Left endpoint. Uh, so let's look at the graph. So that's the graphs. I'm going to draw them quickly. So it may not be very accurate. So I'm going to do a rough graph just to get the idea. Okay, so and then we're going to start with as before 1, 2, and 3. So we have 1, 2, 3. We're going to calculate at the left endpoint now. So yeah, so these are the midpoints. So in this case, what we're going to happen, this is a left endpoint now. So that means that's the point we're going to calculate. That means that's the area. So you don't see anything because it's 0. And for the next interval, we pick the left endpoint. That's the point now we're going to pick. So that means that's the representative area. That's the one you get now. You can see it's completely different. Now again, pick the left endpoint. For this interval, this left endpoint is that one. So that's what you get. So you can see that it's different compared to the previous one. And here, left endpoint is that one. In this interval, so what's the left endpoint? Yeah, it may not be accurate. I think it should be positive. So I'm just using this one. Okay, and then here left endpoint is that one. So you get, so that's what you get. You can see they are completely different from the previous one. So do the same calculation before. Now we remember the points that we have. So this is the x0. That is x1. Like that is the same numbers. Okay. So but new calculation would be. So I'm gonna draw this just for clarification. So this is the interval that we have. So we can start with 0, that is x0. And then we have 0.5, that is x1. We have 1.0, that is x2. And then 1.5, that is x3. 2.0, that is x4. And then 2.5, that is x5. And then 3.0, that is x6. So now what happens, since we pick the left endpoint, your integral start here. So right, your integral start here, the starting point, and for each interval, see, you can see that you're gonna end up here. We don't go for the x6 now. So that means your integral gonna be now. So this is something you need to pay attention. So R6 is not the same. So you can see your index start with 0 now and end up with 5, not like 1 to 6. You can see there are still 6 subintervals, but start with 0 index. So it is f x I delta x. So that's what happened. Okay, so that's different. So now if you expand it, it is f0 delta x, f.5 delta x, like that. Okay, but the last one would be f 2.5. So that's the difference from the previous one. Because last time it was 3.1. Now it is 2.5 because you pick the left endpoint, but that's the left corner. Okay, you can see that's the left endpoint in that interval. Left end. Perfect. Now what you do as before, we're going to calculate the sum. So it is 1/2. 1/2. So you're going to plug in the values. So the first value is 0. The second value is negative 2.875, next one is negative 5, and then 5.625, negative 4, and then 0.625. You don't have the 9 this time. So that means if you calculate this, if you use a calculator, you get negative 8.4375. You can see it is completely different from the previous one. So that's the difference. So depending on the point that we pick, you get different answers. So let's write this as a knot. So what the knot is, so you can see when n is large. So for when n is small, you can see a huge difference between the two. But when n is large, that doesn't happen. Okay, so this is when. So you can write when n is large. Okay, when n is large, roughly like 100 points. Okay, I mean it depends. It depends, but let's say like 100. Like that we can consider as a large number. Large. Then what happen? Those the two numbers that we get for the left hand and right hand point gets very close to each other. So I'm going to say two numbers, two answers. Let's see, that's much better. Two answers. We got two answers. We got are close to each other. Are close to each other. Okay, that's what happened. So that means when n is larger and larger, you can see those numbers getting closer and closer because the error getting smaller. That's what happened. There's an error, but that error gets smaller. So that means those two answers get closer. Okay, it's because of the error. And then when n goes to infinity, that means when you take the limit. So take the limit. They become the same. They become the same and equal to the integral. So that's what happened. That's what the theory part, but we don't do problems from that in this review, but that's exactly what happened. So at least for you to remember what exactly happened. Okay, so that's about that. And then there's a very special case what we normally call the midpoint rule. So what we can do, that's what mostly happen in like calculators. They pick the midpoint, the middle point of each interval, because that's easy to calculate, because you know what the middle point is. If you divide, uh, after you calculate the first one, just add the h or the delta x every time. To get the first number, what you do is you add the x0 and x1 and divide by 2. So that's the first one. After you get the first one, now you know what to do. So that's what we call the midpoint rule. You pick the midpoint because that's kind of okay, because it does, you have a like kind of less error in that case if you pick the midpoint. But if you pick the left hand point or right hand point, there's a huge error. Just to avoid that, what we pick is a midpoint. Okay. So let's write that. That's what we call the midpoint rule. It's actually a theorem. Uh, we don't do problem from that. I'm just tell you what's out there. So midpoint rule. Midpoint rule. Midpoint rule. So what's the midpoint rule? So what we can do is sample points are midpoints. Sample points xi star are midpoint. Okay, that's what happened. You just pick the midpoint and less error. So the reason is less error. I'm going to show you just one situation why there's a less error. So let's look at this situation. Let's say we have a curve like that. Not a straight line. It's a curve. We are looking for curves. So we have a curve like that. Let's say you pick the midpoint. So for these two, so you pick the midpoint. Okay, so you pick the middle point here. So once you pick the middle point, you see it's there. So that's the area we're talking about. And then what happened in this case, you can see there's a overestimate here and there's underestimate there. You can see they kind of close to each other. So they kind of close to each other. So the error is small in this case. So that's the benefit when you pick the midpoint. The error is small. Okay? Error is small because they kind of cancel each other. Not exactly, but there's a pretty good chance that you're gonna cancel. Okay? So that's the benefit. So other things are still the same. So when you start with A, we normally call that as x0, and then x1, x2, like that. And then the last point, which is we normally call B, and then your typical point, what we call the xi bar, as for the midpoint, it is simply half of the n corners. So that means xi minus 1 plus xi. So that is the point we're going to pick for the calculation, the midpoint. You pick the middle point. You add the two and take the half of it. So that is xi minus 1 and that is xi. Perfect. Okay, good. So the formula now is simply, so we can write this one as a to b fx dx is approximately equals to the sigma I going from 1 to n, no limits, f x I bar, the midpoint, delta x. Okay. So delta x is still the same. Delta x is simply b minus a over n, or sometimes we call this h. Yeah, so that is the midpoint rule. So we are not going to do problem from that because it's just the same kind of calculation. So those are the two formulas that we need for the midpoint rule. Good. Let's go to the next one. What we're trying to do is we're gonna interpretation of the integral. So what we call the you have a Riemann sum. You can express this as a integral. So integral representation. Integral representation. Integral representation. So let's do a problem. Let's say express as an integral. Express the limit n goes to infinity, sigma I going from 1 to n, xi cube minus xi sine xi delta x as an integral on 0 to pi. So this is a typical problem. So you identify this as a Riemann sum, and then you know this part, because this is the function part. You evaluate the function. So this is the fi part. If you evaluate the function. So and then delta x becomes dx. So you can write this as the Riemann because it's a Riemann sum. So what we can do, so in this case you can see that fx is simply x cube minus x sine x on the interval 0 to pi. Interval does matter. So that means the problem limit, the expression, we have to rewrite it for completeness, xi cube minus xi sine x1 delta x simply become the integral from 0 to pi. Those numbers goes there. These are the two numbers. The function is x3 minus x sine x dx. So it's a simple problem. So delta x becomes dx. So that's the integral representation. Very simple. Let's just do now let's try to do the backward. So what's the backward? Let's say a problem like this. Express uh, as a Riemann sum. So let's say 0 to 3 x squared minus 6x dx. So what we want to do is, we know that there's a limit, finite Riemann sum, infinite Riemann sum, and sigma. So we have I going from 1 to n. So what's going to happen is, so you know the function, so you're going to divide it into n parts and evaluate at the node point. So the node point we normally represent by I, so it is xi squared minus 6xi dx becomes delta x. And then delta x comma delta x is what in this case? So it is 3 minus 0 divided by n. That's the delta x. So it's a 3 over n. Okay, so that's the Riemann sum representation of the integral. So it's easy. You just represent, you pick the function part, you write it like that with I. Okay, and you also need to know the notation. So let's talk about the geometric interpretation. So geometric interpretation. Geometric interpretation. Geometric interpretation. And we know that by the Riemann sum, the integral, definite integral represents the area under the curve. So it is the area under the curve. That's how we call it, is under the curve. And so it is this area. We normally call it under the curve, but be careful, that's under the curve above the x-axis. Okay, good. So we can use that fact to find certain integrals. So let's look at a problem like this. So let's say evaluate the integral, evaluate the integrals using the interpretation. Yeah, so the goal is to use interpretation. For example, let's look at this problem. So let's say you have an integral which is from 0 to 2 4 minus x squared dx. So if you get a problem like that, what are you going to see? You try to understand what this means. So the one way to look at that is, let's consider this is y. So if this is y, so what do you get? You can see that so y equal 4 minus x squared, and once you square both sides, what's gonna happen? You can write this one as y squared equal 4 minus x squared. If you bring to the other side, this is x squared plus y squared equal 4. 4 means 2 squared. So in other words, this means that it's a circle of radius 2. Okay, so circle of radius 2. So that means if you draw this, so you get a circle of radius 2, so 0 to 2. So what this integral represent? It represent the function part, so that's the y part, from 0 to 2, so that's the height, this is the height, that's the y, so that's equal to that. That means this simply represent this part of the area. That's integral represent that. Simply the area of a quart of a circle. So that means, so you can write this one as, so according to this argument, so it is 1/4 of the circle, or the area of the circle. area of the circle. So that's the geometric representation. But we know that the circle, so it is pi r squared. R in this case is 2, so 2 is squared. So that means it's simply pi. So that means without doing any integrals, you can calculate this complete integral. So it is pi. And actually, you really don't know how to do this problem yet, because that's we can discuss later. So you have to use a trigonometric substitution. Okay, you remember that? So you have to use a trigonometric substitution for that. That's a long process, but here without doing anything you can simply calculate the integral. So that is the kind of way to do a problem like that. Okay, good. Yeah, so you represent the integral as an area. Okay, let's do maybe two more examples in various types. How about this one? Let's say you have 0 to 3 x minus 1 dx, like that. Um, so if you have this, the same argument, so let's try to graph this function. So it is a straight line. Intercept is -1, slope is 1. So like this. Yeah, it's like the slope so with the slope 1. So that's the line. So it's gonna go up to 3, 0. 3, and then you need that when you plug in 1 it is 0, so that's 1 exactly. So what it means is you need this area, uh, the algebraic area. So that means this negative area plus the positive area. So this total area, so you can see one is negative and one is positive. So if you calculate the two areas and add them, so that's what the integral represents. So we can use that idea here. So this line is y equal x minus 1, and if you call this area is a1 and that area is a2, so we know that the Riemann sum, the integral represents the area below the curve and above the x-axis. So in this case it is simply positive area minus the negative area, a2 minus a1. But this one very easy to find. We can find the length here. So you can see when you plug in 3, you get 2 here. Okay, so that means this is simply 1/2 a2. The base length is 2 because 3 minus 1. The height is also 2 minus 1/2. The other one, base length is 1. Height is also 1. Uh, we don't say negative 1, is 1. Okay, because we already put the negative sign in subtract. Good. So that means you simplify, you're gonna get, you can see one of the 2's get cancelled. So it is 2 minus 1/2. So that means 3/2. So that is the integral, 3/2. Okay. So and if you choose a long way, you can see that you get the same answer. So let's do one last problem. How about 0 to 2 x minus 1 absolute value dx? Okay. Even if you want to do this in a regular way, it's difficult because of the absolute sign. You have to split the integral where it makes make a sign change. So now let's look at the graph. So what's the graph here? This absolute function x minus 1 shifted. So we know x minus 1, we know what the graph looks like, but now it is absolute value. So that means what you get is, that's the equation you're gonna get. You're gonna get that part, and what happened, this is gonna reflect. So because of the absolute sign, this part reflect, this gonna reflect. Good. Yeah, so the area is simply area below this part. So that's the area we're looking for because of the reflection. -1, so it's equals to 1. So it's 0, 1, and 2. So and then you can see that by the geometry, because these two triangles are the same size, so what you can do is you can copy this down. So that's the triangle. So what I did is you can put this triangle there. So that means it's going to create a square. So it's simply the area of a square. So you can use that fact. So that means this simply equals to the area of the square. Okay, because that's square. So yeah, area of this square. But that's the same. Good. So that means it is very simple. So you can see it is 1 times 1. So it is 1. So that's the how you use a geometric idea to do the integrals is 1. Uh, good. So I'm going to give you some problems for you to try. So these are something that you can try. So so uh, so how about this one? So this is 1b. So you can try negative 4 to 4 to x minus 16 minus x squared square root dx. That's 1. And 1c 0 1 to x minus 1 absolute value dx. Okay, let's try these two. You can find the answer in the description. So the last thing what we can do is we can talk about the properties of the definite integral, because we use that everywhere. So this is a recall of what we did. Uh, so the properties of definite integral. That's the last thing we do. Uh, Properties of a definite integral. Um, so the first property is if we integrate from a to a, so this integral has to be 0. The second one is if we have a to b fx dx. So what happens if you switch the numbers? So it is b to a. So it is simply negative of that. So these are useful for certain problems. And part C, if you have a sum or a difference, so if you have fx plus or minus, depending on whatever the sign you have, so what you can do is you can split that the same way. So it is a b fx dx. If it's a plus sign, use a plus sign. If it's a minus sign, use a minus sign. And then a to b gx. So you can split the integral. And then also, if you have a constant multiple, you can pull the constant out. So a to b c times fx dx equals c, you pull out, is a to b fx dx. And the last one is you can split at another point in the domain, not necessarily in between a and b. So if you have a to b fx dx, so what you can do is you can pick another point c in the domain. So like this. So let's say you have a and b. So you can pick another point which is either inside or outside, doesn't really matter. Only condition is c has to be in the domain. That's it. If c is if all if the function has to be defined in this complete interval. Okay, that's the only condition. Like, you know, so it can even be like this. So a b, let's say c is outside. If the function defined in this whole interval, then everything works. Okay, it will be integrable in this whole interval. If this is the case, what you can do is you can go a to c fx dx and then plus c to b fx dx. So you pass through another point in the domain. So this is like those are the like properties that we can use for definite integrals. Okay, so that is about definite integrals. Next, we're going to talk about the fundamental theorem of calculus. Very important topic. So next, we're going to talk about the fundamental theorem of calculus. So number 2, the fundamental theorem of calculus. Fundamental theorem of calculus. So in short, we call this FTC, fundamental theorem of calculus. Okay. So F, T, and C. So let's try the theorem. So theorem has two parts. So let's talk about the first part. So theorem, part 1. So F, T, C, part 1. So what the part 1 says, if f is a continuous function, if f is continuous, if f is continuous on an interval a to b, then the function defined by an integral like gx, which is a to x. So a is any point inside the interval, not necessarily a. So a to x, ft dt, ft dt. Then what it says that this function is continuous and also differentiable. So is continuous, CTS, continuous on the closed interval AB and differentiable on the open interval AB. Okay, so it's very important. On the closed interval, it is continuous. On the open interval, it is differentiable. So only condition that we need is it has to be continuous. And so the most important part, and if you take the derivative of the integral a to x ft dt, we know that this is a function of x, so you take the derivative of that. What it says that it is simply you replace t by x. Only thing about a is it has to be in the domain uh, where the function is continuous. That's the only condition. So that's what we call the fundamental theorem of calculus part 1. Okay, this is very useful if you want to find derivatives of certain integrals. So let's start with a interesting problem. So this is the first one. So example, find the derivative of this one gx, which is going from e to x, let's say 1 over t natural log t the fourth root dt, something like that. So 1 over t the fourth root of natural log t dt. Good. So let's try to find the derivative of this one. So what is the, so I'm going to do this in two different ways to compare. Method 1, just let's try to find the integral first. That's the obvious way to do it. Let's find the integral, and then once you get the integral, let's try to find the derivative. So let's do that. So the first thing is how to integrate this one. So you can see that we have to use the substitution method for this problem. So I'm going to use the substitution method. So I'm going to take let u equal the inside function, in this case ln t. So you can pick that. That's the substitution you need. And then what's going to happen is, we know that after that du, take the derivative, du is simply 1 over t dt, and you can see 1 over t dt is right there. And also we need to find the limits. So what are the limits when t equal e, u equal ln e, which is 1, when t equal x, u equal ln x, yeah, we replace t by x, so you get ln x. That's what you get. Now what we can do, we can integrate the function. So gx is simply, you can see it is e to x 1 over t ln t to the fourth root dt. So we have dt. Now let's substitute. So what happened? E becomes 1, and then x becomes ln x, and then here what's going to happen? You can substitute. So you can see that we have 1 over t dt. 1 over t dt is du, so that means this simply becomes 1 over u to the 1/4, and then 1 over t dt is du. So that's what you get. That's what we are doing. Now you can rewrite this one as 1 to ln x u to the negative 1/4 du. So this is just the basic power rule. So you add 1. When you add 1, it's become 3/4, and you divide by that. That means you multiply upside down. So that means it's going to be 4/3 u to the 3/4 evaluated at ln x and 1. That means you're going to get 4/3 ln x to the 3/4 minus, you plug in 1. When you plug in 1, is any powers 1 is 1, so that means you simply get 1 4/3. So that's the integral. Now what are you going to do? You need to find the derivative of that. So let's find the derivative. So that means d over dx, gx is the derivative of that. So the d over dx. So let's write it 4/3 ln x 3/4 minus 3/4. So if you take the derivative, that's a constant. So you have to use a chain rule. So let's use the chain rule. So you're going to get 4/3. So by the chain rule, it is 3/4 natural log x. You subtract 1, so negative 1/4 times multiply by the derivative of the inside function, which is 1 over x. That's what you get. And you can see these get cancelled. So you get simply so you get 1 over x ln x to the 4th root. So that's what you get as the answer. And once you see that, you can see if you compare that with your original problem, that's exactly that. You simply replace t by x. So that means everything we did so far is pretty much useless. That's exactly what the fundamental theorem of calculus says. It says that you simply need to replace t by x. That's exactly what's going to happen here. So you don't want to do that. So what I'm telling you, you can see it's a long process, but don't do that. You don't want to do that. You can just simply replace t by x if the function is continuous on the domain. So this is a lesson. Okay, so that means this is a long process. This is really unnecessary. You want to do simply replace the t variable or whatever the variable by the variable given here, in this case x. So you can see it's match very well. So now let's do it that way. So the part 2, so let's using the fundamental theorem calculus. So what we can do, you can say since the function ft in this case which is 1 over t natural log t to the 4th root is continuous on the interval e to infinity. Okay, so e to infinity, so it's continuous over there. So what we can do is, by the fundamental theorem of calculus, say FTC, what's going to happen is the derivative of the integral e to x 1 over t ln t the 4th root dt is simply you replace t by x. So that means 1 over x ln x the 4th root. So that's it. Okay, you don't want to do anything, just replace that one. So that is the benefit of using the fundamental theorem of calculus. So let's do a few more examples. I want to show you the benefit of that. So let's do like another problem. So find the derivative of Find the derivatives of. So let's do the first one. So let's say gx equal -1 -1 to x t 1 plus t squared square root dt. And you can see when you look at this problem, you feel like you want to integrate. That's not a good idea because you don't want to do that here because you are taking derivative of an integral. So you can use the fundamental theorem of calculus. So again, we use the idea. So we can say since the function inside function ft, which is t times 1 plus t squared square root, is continuous on the interval from -1 to infinity everywhere, is continuous on that by the fundamental theorem of calculus. You can say FTC. So g prime x is simply, the derivative of that is simply, yeah, I'm going to write this one like that until you get like comfortable. So d over dx, the integral -1 to x t 1 plus t squared square root dt is simply, you replace t by x, so it's x 1 plus t squared, not t, 1 plus x squared square root. That's it. Okay, so very simple, just one line. So let's do another one. B. So how about this one? Let's say hx equal to 0 to cosine x, 0 to cosine x 1 minus t squared dt. How to do this problem actually? So you can see that this is not easy because you can even use the substitution method here, the basic substitution method. So you have to use the trig substitution for this problem. So it's like a lengthy process, really lengthy process. So we are not going to do that. You don't need it. We can use the fundamental theorem calculus for this problem. But you can see something different here. You can see this is not x, this is cosine x. So when you see something other than x, what you want to do is you want to use a the chain rule for that. So let's do that. So the first step would be, we can say let u equal whatever the function you have here, cosine x. So we're going to pick that and then take the derivative. That's the next step. So then we have du equal du by dx, because we need everything here. So then what happened, du by dx as a cosine, so negative sine x. That's what we get. And then again, so in the inside this interval the function is continuous, so we can say by, so again since ft, which is 1 minus t squared square root, is continuous by the fundamental theorem of calculus, we can write this one as, so h prime x is, so what we have, what we need to do here is, so this is simply the derivative dx 0 to cosine x. I'm gonna write all these steps here, especially this is the first problem. What's the first step? You can replace. So we can write, dy dx. You can replace 0 to cosine x u, then 1 minus t squared square root dt. Now you can see that this is the integral is a function of u, but you try to take the derivative with respect to x. So that's the problem. It's a function of u. You try derivative with respect to x. So that's when you use the chain rule. So what you can do? You can introduce the u variable to the derivative. So you can write this one as like this. So what do? You to d over du, the integral from 0 to u, 1 minus t squared square root dt times by the chain rule. This times you're going to multiply by du by dx. So that is the chain rule. Okay, chain rule. So we have that, and then this part you can do using the fundamental theorem of calculus. So we can use the fundamental theorem of calculus now for the first part. So that means so what you're going to do is you replace the function t by u. So that means it's going to be 1 minus u squared square root times du or dx. We already get it is negative sine x, negative sine x. I put the parenthesis because it's a negative sign. Now you're going to replace u by your function is a cosine x, so it is 1 minus cosine squared x square root. You can put the negative sign in front, or still leave it like that. Now what's going to happen? We know that 1 minus cosine squared, this means sine squared. Once you do the square root, it's going to be sine, so it is negative. You get one sign here, another sign there, that means sine squared x. So that is the final answer after simplification. So you can write it like that. Good. So let's do another problem. So as the next example, let's do the this one. Hx equal square root x to 1 z squared, doesn't look like z squared over c to the 4th power plus 1 dz. Good. So if you look at this problem, there are two problems. One is it is not in the right format. We know that when you have the integral, it has to be a to a function like that, but it is not. So that's one problem. The other problem is it is not x, it is square root x. So there are two problems here. So the first problem we can remove by switching. So we can say negative. We can write this one as 1 to square root x. So the first problem is over. You switch the integral, put a negative sign. C squared over c to the 4th plus 1 dc. We discussed this one, switching, in the previous one. When you talk about definite integral, that's one of the property. Now to handle the other one, we can use the substitution. Okay, so we're gonna say let u equal square root x. Then we have du by dx is 1/2 x to the negative 1/2. In other words, 1 over 2 square root x. So we get that. Now we can use the chain rule. So it is d over dx, the integral square root x to 1 z squared c to the 4 plus 1 dz, which is negative d over dx 1 to the square root x z squared c to the 4th plus 1 dz, and then negative, we can write this one as a integral of we can replace x by u, so it's 1 to u z squared c to the 4 plus 1 dz. Now we use the chain rule, so negative, we can write a integral we take derivative with respect to u, so 1 to u z squared c to the 4th plus 1 dz, and then times the du by dx, that's coming from the chain rule. Now for the first part we can use the fundamental theorem of calculus, so we can do FTC here. So we have negative, replace, because we know that this function is continuous. Yeah, so this function is a continuous function on the domain. Okay, so this is continuous. Good. So that means you can replace z by u. So that means it's going to be u squared over u to the 4th plus 1 times du dx. We already found is 1 over 2 square root x. So we plug in for that. Now replace u by x. So if you plug in that, so it is negative. This is a square root x squared Some of these steps are not necessary, but I'm writing it for clarification purposes. So it is 1 over 2 square root x, and you can see you can simplify this one of the square root x get cancelled. So you get 1 square root on top. In the bottom, this is square root x, you multiply by 4 times, so that means it's going to be, and then we have 2 here, going to be x squared plus 1. So that is the final answer for this problem. Okay, so it's not that difficult, but you can see this is what you get. Okay, so that's about that. I'm going to give you 2 problems for you to try, so you can try this problem as exercise. So exercise. Uh, so we have these two. So we're going to say find the derivative of find the derivative of so the first one, which is 2a gx equal 1 to x ln 1 plus t squared dt. That's the first one. And then 2b, let's say y, which is 1 over x to 4 1 plus 1 over t square root dt, and then 2c, so we can say hx is we have tan x 0, let's say e to the negative t squared dt. Okay, you can find the answers for this in the description. Now let's go to the second part of the theorem, fundamental theorem of calculus part 2. So theorem. So the fundamental theorem of calculus part 2. So what it says, if f is continuous on the interval ab, then it says that the integral a to b fx dx is simply equals to fb minus fa, minus fa, or we write this one as fx vertical bar ba, or sometimes if it is a long expression we put a bracket, we write fx like that. So we can use any notation depending on how complicated it is. So everything are the same. So where f is any, f is any antiderivative, f is any antiderivative of f, any antiderivative of f. So that means what? That is if you take the derivative of f prime, you get a small f. That's what antiderivative means. If you take the derivative, you get the function. So this is what we call the fundamental of theorem part 2. Okay, so that means the integral is simply equals to definite integral is simply equals to, you find any antiderivative and then you subtract, you plug in the b value first, the top value first, you plug in the top value first and then the bottom value, and you subtract the two. Okay, so it's important. That's the first top value, that's the bottom value. Good. So this is the fundamental theorem of calculus part 2. So let's put inside that. Good. It's important. So what we can do, we're going to solve a few problems from that. Good. So let's say evaluate. The first one is, let's say 3 to 6 1 over x dx. So what are you going to do? We learn antiderivatives in Calc 1, so we're going to recall that. So this is also coming from the table of integrals that you can find the link in the description. So make sure that you understand, you remember those things, because those are like kind of common ones. So look at the description for a link for the common integrals. So that's where these are coming from. So 1 of x, when you say 1 of x, we know that it is natural log x, that is the antiderivative of 1 of x, and then we're gonna put the values b and 3. We're gonna evaluate at b and 3. I'm sorry, not b, 6 and 3. Yeah, it's easy to forget. Okay, 6 and 3. So that means you plug in 6 first, minus you plug in 3 next. So this is, you plug in that first, and then you plug in this, that goes next. Okay. So order matters. Okay, now how to simplify this one? We know that log difference is the log division. So this is simply log 6 over 3. 6 over 3 means 2. So that means final answer is ln 2. So that's what you get. B, how about this? 0 to 4 t squared minus t 3 halves. For a problem like that, this is like a simple problem. You can use the power rule. Also, according to the power rule, so this is t squared, that means t 3 over 3 minus, again you add, so you begin 5 half, that means 2/5 t 5 half. There are more, so I'm going to use the bracket notation, 4 and a 0. So that means you first plug in 4, so it is 4 to the cube minus over 3 minus 2/5 4 to the 5 half minus 0, because we're plugging 0, all 0. Now how to simplify? This is 4 to the third means 16, not 16, 64. 4 to the cube, so it is 64 over 3 minus. Okay, how to simplify this part? When you have something like that, what you're gonna do is you're gonna take the root first. So that means 4 half, 4 square root. 4 square root means 2, and then 2 to the 5th power. That means 32. So you're gonna get 2/5 times 32, and you can see that is 64. So if you pull 64 out, you get 1/3 minus 1/4. Take the common denominator, so you get 5 minus 3, so 2. So that means your final answer is 128 over 15. That's what you get. Okay, good. And if you don't understand any of them, you can put that in the description. I'm going to put the solution there. Okay, so I'll put the timestamp and ask, like, if something is not clear. Good. So that's about that. So let's do more. How about this problem? So let's say C 0 to 1 u plus 2 times u minus 3 du. That's what you get. So you can see there's a product here. Unfortunately, there are no product rule in integral calculus, so no product rule. No product rule in integral calculus. So therefore, what you're going to do is you're going to expand. So what we're going to do, we can distribute it. So you're going to multiply through, so you're going to start with first one, multiply with the 2, and then start with the other one, multiply with the 2. That's what we do. Or you can use a FOIL. So if you do that, so you're going to get 0 to 1. If you multiply, you're going to get u squared, and then you have u times -3, 2 times u, so that means you get negative u, and then -6, so you get du, and then we can use the power rule, so the u 3 over 3 minus u squared over 2 minus 6u. So there are more, so we with the bracket notation, so 1 to 0. So if you plug in 1, you get 1/3, 1/2 minus 6 minus 0, And if you simplify, you can take the common denominator as 6. Um, Actually, if you simplify the first two, you're going to get 1/3 minus 1/2 means 1/6, which is negative. So that means a negative 6 1/6. That's what you get. You can leave it like that, or you can write it as the improper fraction. But this is better. So that's how you do it. And what you want to remember is there are no product rule in integral calculus. Okay, let's do another one. How about this? Um, let's say 1 2 3 y cube minus 2y squared minus y over y squared dy. And again, there are no quotient rule. Okay, so no quotient rule. So there are no quotient rules. So that means what you're going to do first is you're going to divide by y squared. So we can rewrite it. So it is 1 2 3. If you divide by y squared, you get y. If you divide by y squared, you get 2 minus 1 over y. That's what happens when you divide by y squared all the terms. Now what we're going to do, we can integrate one by one. First one is by the power rule, y squared over 2. Next one is the simple the constant, so it is you just multiply by the variable, and then minus this is natural log. That's how you get more terms, 3 and 1. So let's plug in 3 first. So it is 3 squared over 2 minus 3 times 2 means 6 minus ln 3. That's the first one, minus the second one. Plug in 1. 1/2 minus 2 minus ln 1. ln 1 is 0. So this is gone. So if you simplify, this is how much you get? 3 squared means 9 over 2 minus 1/2. That means 4 over 2. That means 4. And then we have plus 2. So that means 6. That's cancelled with the negative 6. So that means all these get cancelled. So this, that, and that get cancelled. So you only get negative 1/3. So negative ln 3. In other words, if you bring the negative sign inside, you can write this ln 1/3 as the final answer. Good. E. So how about this one? It is 0 to pi over 3 secant theta tan theta d theta. And you can see this is like coming from the table directly. We know that the secant theta tan theta is the derivative of the secant theta. So that means the antiderivative is simply secant theta evaluated at pi over 3 0. And how to do that? You can plug in the value, or you can write secant as cosine. So you can write this one as 1 over cosine because you know those values. And then pi over 3 0. So let's plug in cosine pi over 3. So it is 1 over cosine pi over 3 minus 1 over cosine 0. Cosine pi over 3 is 1/2 minus 1 over cosine 0 is 1. And then 1 over 1/2 means 2 minus 1, that means 1. So answer is simply 1. Let's do 2 more examples before we go to the next section, next topic. How about this one? F 0 1, let's say x to the e plus e to the x dx. Again, x to the e is a constant, so that means we can just do it using the power rule. So it is so what's gonna happen is x, you add 1 and divided by the same power, and then plus ex is ex, that we know. More functions, so we put the bracket 1 0. So let's plug in 1 first. So if you plug in 1 first, you're gonna get 1 to any power is 1. That's e plus 1 plus e1. That's what you get from when you plug in 1 minus plug in 0. When you plug in 0, x2, this is 0. 0 to any power is 0, so it's gone. And then So you plug in 0, so this gone, and then plus e to the 0, which is 1. So that means if you simplify this, what you get is, you can see e to the 1 is e, and then e minus 1. Okay, so you're going to get 1 over e plus 1 plus e minus 1. So we can simplify this. When you multiply these two, what do you get? You get 1. And then when you multiply e plus 1 with e minus 1, there's a different squares. So you're going to get e squared minus 1 divided by e plus 1. And you can see this get cancelled. So the final answer is simply e squared over e plus 1. So you can simplify up to that. Let's do one last problem. So how about this one? It is 1 over square root 2 1/2 4 divided by 1 minus x squared square root dx. So again, you can look at the tables. This is one of the formula in the table. When you have 1 over 1 minus x squared, means that is sine inverse x. So that means this is simply 4 sine inverse x is coming from the table, okay, by the table. So please look at the description for a link for the table if you forget that. And then we can evaluate at 1 over square root 2 and 1/2. So what does that mean is, so it is a 4. 4 common, so it is sine inverse 1 over square root 2 minus sine inverse 1/2. And we know that from the common trigonometric tables, sine inverse 1 over square root 2 means pi over 4, and minus 1/2 means pi over 6. And then you can simplify these two. So take the common denominator in this case, which is 12. So so it is 3 minus 2, so it is pi over 12. So that means so you're gonna get, so you can see that if you write, so this is simply 4 times pi over 12, and you can simplify, so you get pi over 3 as the final answer. And then you can do these as the practice problem. So you can say, I'm going to give some exercise. So evaluate. So this is 2. This is 2D. So 2D is let's say 1 to 8 x to the negative 2/3 dx. 2E is 1 to 2 v cube plus 3v to the 6th over v to the 4th dv. To f is, let's say, square root 3 1 over square root 3 8 divided by 1 plus x squared dx. Okay, so let's try to do these three as practice problems. Next, we're gonna move on to before we go to the next section, actually I want to discuss these two special problems. So my question is, what is the wrong with this argument? Okay, so what is wrong with the argument? So for example, the first one, let's say you want to evaluate -1 to 2 1 over x squared. So if you did not think too much, You can just integrate the way we normally do. So it's 1 over x squared. That means integral is, you can bring it to the top. So it is x to the negative 1 over negative 1. And then you evaluate at 2 and negative 1. And if you do that, what do you get? So it is negative 1 over x. Uh, so it is negative 1 over x evaluated at 2 and negative 1. So if you do that, you get negative 1 half on the first one. And then we have negative, negative, positive, and then put negative 1 again. So you're going to get negative 3 halves. But the interesting thing is this answer is wrong. So this is not the answer. So one of the reason is, let's look at the graph. So if you look at the graph of this function, so you're going to see that this is what you get. So it's going to go to, it's 1 over x squared. That means both are positive on side, but when it goes to 0, it goes to infinity, like that. So it's gonna go like that on this side, and also the other side is gonna go like that. So that means if you try to evaluate between the two values, between negative 1 and 2, so you can show that actually this area is infinite. There's infinite area like that. So that means there's a wall like that. How much paint you need? You need the paint in the entire world. Still, you have a wall. So it's like that. So the area is infinite in this case. Okay, you can show that. So area is infinite. That means the integral is infinity. That's what you get. So we cannot discuss this problem yet. We have to wait until we talk about what we call improper integrals. Though what's the problem here is, we know that when you want to use the fundamental theorem of calculus, the function has to be continuous in the entire domain. But that's not the case. This function is not continuous at 0. So that means if t, in this case, 1 over t squared is not continuous at t equals 0. So that's the problem. At t equals 0, so we cannot use the fundamental theorem here. So we cannot use fundamental theorem of calculus part 2 here. Okay, so that's the problem. So it doesn't work. And then I want to give you one more example, just for the curiosity. How about if you have a problem like negative 1 to 8, 1 over x cube root dx. And you can see that we have a very similar problem here as well. So what is the graph of this function? This is a cube. That means positive, when positive is positive, when negative is negative. So the graph looks like this. So this is the shape of the graph. So what happened when x goes to 0, it goes to infinity, so it's going to go like that and goes to 0. On the other side, it also goes like that. So that's the shape of the graph, symmetric. And then again, we can evaluate at negative 1 and 8. So if you try to find the area now, and you can show that it is a finite number now. Even though this graph goes to infinity, there's a finite area. Okay, so in this case it's not infinity, you get a finite number. So if you do by mistake, like let's say you did it in the wrong way, because we know that the function is not continuous. Okay, so this is not continuous at 0. So not continuous at 0. So if you, let's say you by mistake you write it the same way. So this is negative 1 to 8 x to the negative 1/3 dx. So that means you can use a power rule. If you use a power rule, you get 3 halves x to the 2/3, x to the 2/3, and then you can evaluate at 8 and negative 1. So it is 3 halves. So 8 2/3 minus negative 1 to the 2/3. So if you do that, what do you get? You get 3 halves. Okay, how we do this? Let the root first. So if you take the root, the 8 cube root means 2, square means 4, so you get 4 minus the same thing, negative 1 cube root is negative 1, square means 1. So you get 1 here. So that means you're gonna get 9 half. Actually, that's exactly the answer you get, but the method is completely wrong. So you can't do it because this step is not valid. Uh, this step is not valid. We have to do it in a different way. So what I want is wrong method. Okay, wrong method. So we can discuss this problem in the improper integrals. So we can discuss this problem later. So improper integrals. So when we discuss that, we can do the correct method and get the answer, but you will be surprised that you will get the exact same answer, but completely wrong method. So you cannot do this because this function is not continuous at some point in the domain, in this case 0. Okay, so that's the problem with that. Okay, so now let's go to the new section. So next talk about indefinite integrals and the net change theorem. So what's indefinite integrals? We already know this one, so I'm going to rewrite it here. So when you have fx dx, so if you integrate fx, so we can write this one as uppercase fx. To exaggerate, I'm going to add a c to mean that this is the most general antiderivative. So so that's the formula, and fx is any antiderivative, and we add a c, and then so this is what we call the general most general antiderivative. Antiderivative. So that means always contains a c in there with the most general one. And fx is any antiderivative. So fx, the uppercase fx is any antiderivative. Any antiderivative. So let's write few common ones. So not all ones. So few common ones. So so common antiderivatives. Common. So these are a few common ones. What is the most important one is the power rule xn dx. So this is x n plus 1 over n plus 1 plus c. So this works when n not equal to negative 1. If n equal to negative 1, this looks like 1 over x dx. So this is the natural log x plus c. Those are two very important ones. And then we have the exponential function ex, so which is ex plus c. And the for other bases, if you have base b, bx dx, so which is bx divided by ln b plus c. And then sine cosine, so we have sine x dx. So sine means negative cosine x plus c. So when you have cosine x dx, which is sine x plus c, and then we have those inverse functions. So 1 over x squared plus a squared dx, so which is 1 over a tan inverse x over a plus c. And then we have let's see, we have 1 over a squared minus x squared square root dx, so which is, there's no 1 over a here, this is simply sine inverse x over a. So this is not the complete list. So look at the description for a list of 22 common integrals. So the table of integrals, table of integrals, you can find the link in the description. Okay, so go to the description, find the link, and those are the common ones. There are 22, so these are just the basic 8 ones. So let's try to use this in some problems, even with the other ones. So how about this? So let's say problem. evaluate. So evaluate A. So let's start with 15 x to the fourth minus secant squared x. So what we can do, we're going to match with the table. First one is the power rule, so we can use that. So it is 15. So you add 1 divided by that number minus secant squared. Secant squared means that's a derivative of tangent. So that means it is tan x, and then we add a c. If you can simplify, so here we can simplify. You can see 5 and 15, so you get 3. So that means it's 3x to the fifth minus tan x plus c. So that's the first one. So let's do a couple of other examples. So let's say let's do a definite integral as well. So let's do this definite integral. So 2x cubed minus 6x plus 3 x squared plus 1. So it's again, this is not that difficult. So it is 2x to the fourth divided by 4 minus 6x squared divided by 2 plus this is 3 tan inverse x. So we can evaluate this at 2, 0. So if first plug in 2. Actually, let's simplify this first. So if you simplify, you get x fourth over 2 minus 3 x squared plus 3 tan inverse x. So it is 2 and a 0. So let's first plug in 2. So you plug in 2, so 1/2 2 to the fourth power minus 3 2 squared plus 3 tan inverse 2. And when you plug in 0, you can see all the terms are 0, so it's gone. And when you simplify, you're gonna get 3 tan inverse 2 minus 4. So 3 tan inverse 2 minus 4. We normally have the negative ones later at the end. Okay, how about this one? Number C. So cosine theta divided by sine squared theta. So when you get some trigonometric expressions like that, sometimes what you have to do is you have to simplify them into a formula that you already know. So for example, if you split this, if you write this one as cosine theta over 1 of the sine theta and 1 over the other sine theta d theta, and you can see that the first one is cotangent theta, this one is cosecant theta. This is one of the formula in the table because this is the derivative of the negative cosecant theta. So this is negative cosecant theta plus c. So it's simply coming from the table. So this is a familiar one. So what you want to do is you want to rewrite the integral so that it is something familiar. Okay, so let's do another problem. Problem number D. How about this? 1/4 2t squared plus t squared square root t minus 1 over t squared. And we already know that there are no quotient rules. So what do you want to do? You can't integrate the top and bottom separately. No, that's not going to work. So what you want to do is you want to simplify this first. So I'm going to simplify the integrand. So you can divide by t squared all the terms. So we divide by t squared all the terms. You get from the first term you get a t. From the second term, if it is cancel t squared, you get square root t. From the last term, you get negative 1 over t squared. This you can write as t to the negative 2 because that's gonna make it easy to do the integral. So we write it like that. Now you can use the power rule. So from the first one 2t here, if you use the power rule, this is t to the 1/2, so that means you add 1, so 3/2, so it's 2/3 t to the 3/2 minus same thing, you add 1 to the negative 1 divided by negative 1. So that's what you get, and you evaluate at 4 and 1. So you can evaluate at 4 and 1. So let's add 4 first. So if you add 4, so what do you get? If you add 4, you're gonna get 8. 8 plus 2/3 4 to the 3 halves. That's easy to simplify. And then negative, if you add for negative and positive, so it's 1/4. That's what you get when you add 4. If you add 1, this will be 2 plus 2/3 plus 1. So that's what you get. And only difficult one would be this one. This is easy to integrate, easy to evaluate, but you go with the square root first. So the 4 1/2 power, that means 2, and then you cube it, so you get 8. So that part is simply equals to 8. Okay, and then once you simplify everything, you should end up getting what do you get? You're gonna get 5 plus 1/4 plus 14 thirds. That's what you get. If you simplify this one, you're gonna get 109/12, and you can simplify this further. Okay, let's do one last problem. E. So how about this one? So everything 2 to the x minus 3 over 4 minus x squared square root plus tan squared x. Unfortunately, tan squared x is not something common, so we're going to rewrite this with something that you know. For example, using a trigonometric identity, you can write this one as secant squared minus 1. The reason is secant squared is simply, secant squared. Secant squared is simply, secant squared x is simply 1 plus tan squared x. So that means tan squared x is secant squared minus 1. So we can rewrite it like that. So we can rewrite 2 to the x minus 3 over 4 minus x squared square root. And then this one we can write as secant squared x minus 1. Now you can see that you can integrate term by term. So the first one is 2 to the x over ln 2. This one is 3 sine inverse 3 sine inverse x over 2, because it's a 4, so that means x over 2 with a squared, so a is 2, and then secant squared means tan inverse, not tan inverse, tan x, this is tan x, and minus x plus c. You can see you cannot simplify this, so you can leave this as the final answer. Okay, so you can do all of them just looking at the table. So that's about indefinite integrals and some of the definite integrals. So you just use a table. Sometimes you need to simplify. So let's look at the application side of this one. What is that? The net change theorem. So let's talk about that. So the net change theorem. Net change theorem. Net change theorem. So what the net change theorem is, that it says the integral of the rate of change is the net change. The integral of a rate of change, the integral of the rate of change, integral of the rate of change so if you integrate the rate, integral of the rate of change is the net change, net change. So that means if you integrate the derivative of a function, so if you integrate the derivative of a function, so you get the net change of the function. That's the derivative. So you get the net change of the function. So it is fb minus fa. So that's the net change. So that is the net change theorem. So that means if you integrate a rate of the change of the function, you get the change in the net change of the function. So that's the net change. So this part is the net change. Good. So there are some nice applications of this one. So let's talk about some applications. So let's exaggerate this one. So what it says, if R, so we can say R for rate. So RT is the rate of the change of a quantity, is the rate of change, of change, the rate of change of a quantity. So whatever that, so it is A to B, the rate, you integrate the rate. So so you get the change in the function. Okay, so it's just a rewriting of what we have over there. So this, if you explain this, so this is the change, because from B to A, that's a change. So change in the quantity, from, let's say x is a variable, from x equal A to, actually here is so from t equal A to t equal B, from A to B. So something changes from A to B. So the question is how much is change between the two? You integrate the rate. So some major applications would be the velocity and displacement problems, and this is also used in like physics and chemistry, especially if you know the rate of change and then you integrate, you get the change in the quantity. So so one of the major application would be, so let's say if an object, let's say if an object is moving, along a straight line, if not a straight line, the calculation will be a little difficult. Along a straight line, let's say with the position, straight line with uh, the position given by st, its velocity, its so its velocity is, we know that we write this one as vt. So its velocity is s prime t, we write that. So we know that if the position, then we can find the velocity by taking the derivative. So now the question is, if you integrate, this is from t1 to t2, the velocity, see that is uh, the rate of change of the displacement s prime t by the net change theorem. What we get at the end is st2 minus st1, the change in those two directions. So this is simply the displacement. Okay, displacement between the two time interval t1 to t2. So how much displacement? Because if it's the velocity, you get the displacement, not the distance. Okay, if it's the velocity, you get the displacement. And then so for distance, so if you need the distance, so let's say you want to find the distance traveled. So if you want the distance traveled, what you're going to do is you integrate the speed. That means you integrate the absolute value of the velocity function. If you do that, you end up getting the total distance traveled. So total distance traveled. So here you have to be careful. If you need the distance, you need to take the absolute value. If you need the displacement, you just integrate the velocity function. Okay, because once you take the absolute value, this is simply speed. So if you integrate the speed, you get the distance. If you integrate the velocity, you get the displacement. So what's going to happen in this case? So if you look at the graph, let's say it's going to be positive and negative and positive like that. What you're going to do is take the absolute value. That means it's going to reflect to the top. So that means what's going to happen every time you add all the time. So that's why it's the distance rather than displacement. Because displacement can be positive and negative. the distance is always positive. So that's why you have to take the absolute value. So then it's going to reflect it. So you simply add from the point A or from T1 to T2. Okay, that's how you take the, so that's the velocity graph. So take the absolute value, it becomes the speed graph. Okay, the top one is the speed one. Okay, good. And then for the acceleration, so we know that the acceleration is, at, which is the velocity of the which is the derivative of the velocity. So that means if we integrate from t1 to t2 the acceleration, since this is the derivative of the velocity, what you get is a change in the velocity. That's what you get, change in the velocity. So that's a change in velocity. Okay, change in velocity. So this is like one nice application of that. So let's just do one example just to make sure that we understand how to do the problem. Only one example. Okay, so let's do this one. So the example is, let's say a particle moves along a straight line. A particle moves along a straight line, with velocity vt is given by some function, let's say t squared plus t minus 6 meters per second. That's the unit, t squared plus t minus 6 meters per second. So let's ask two questions. Find the displacement during the time period from 1 to 3. Okay, and then 1 to 3, and then find the total distance traveled in the same period. Find the total distance traveled, total distance traveled during the same period of time. Okay, so let's see the difference, why you get two different answers. So the answer, so the first part, we know that the displacement is simply the integral of the velocity function. So 1 to 3, 1 to 3, that's the limit. Just integrate the velocity function. You don't have to do much, just the velocity function. So if you do that, so we plug in here, so 1 to 3 t squared plus t minus 6 dt. This is a very easy integral, so it is t 3 over 3 t squared over 2 minus 6t, and evaluate at between 3 and 1. So you plug in 3, so you get 27 over 3 plus 9 over 2 minus 18. That's the first one. And then minus, you plug in 1, so 1/3 plus 1/2 minus 6. If you simplify, you simply end up getting 2/3 meters, because that's unit. So you get only 2/3 meters, less than a meter. That's the displacement. That means how much you move from the first one to the other one. And you can see that at the beginning, at t equal 1, so what are the factors actually? What are the factors of this function? Let's factor this. If you factor this, you're going to get t plus 3, t minus 2. So that means the time you can see so negative 3 and 2, but you're going to start at 1. So we're going to looking at 1 to 3. So that means you can see uh, this function is negative between -3 and 2. Uh, yeah, because if you graph it at 2 it is 0. This is like concave down function. So the graph of the function is gonna go down and up. It's gonna go down and up like that. So that means from 1 to 3, you can see there's a sign change. So there's a sign change from 1 to 3. At the beginning is negative, so it's going to go backward. And so that means if you look at the movement on the straight line, so how it move? So the straight line. So when you start at 1, you can see it's negative. Velocity is negative. It's going backwards. It's going backward and stop and come back. So that's what happened. So that's how it move from 1 to 3 time interval. 1 to 3. So that means at the end, displacement would be simply this part. So it says that it is only 2/3 because the velocity is negative at the beginning. If you measure this way, it's going backward because velocity is negative function. It's going backward and then stop and come back. See at 2 it stops. Okay. And then it's gonna come back. So at the end, so you only see a displacement to, and you can see it's traveled a lot. So that means you should get a larger value for the total distance travel. So let's do that. So part B, the distance is again 1 to 3, but now the absolute value function, the speed function. You integrate the speed. So as before, so we noticed that this function between -3 and 2, so it's gonna go down and come up. So like that. So between 1 and 3, so it's negative from 1 to 2 is negative. That means what we normally do is let's draw it properly. Yeah, let's draw this properly. So so we have, so you can see the factors are zeros are -3 and -2. So we have, what we have is we have t squared plus t minus 6. You can factor this as t plus 3, t plus 3 and t minus 2. So that means you get -3 and 2. So at those places it gets 0. So that means there's a 1 at 1 0 at there and another 0 at 2. So that's what happened. So that means if you look at the graph, so it's gonna go like that, 0 and come back. So it's like that. That's the 2. And then this you can see this is 1 and 3. Okay. So yeah, that means our interval is, we are interested in only in this interval 1 to 2, and you can see at 2 it's negative. It's negative. That's why it's go backward. And then you're gonna come to the other side again. So what we can do is we can split the integral where it makes 0. That means we write this interval as 1 to 2. Take the absolute value of the function. So absolute value of t squared plus t minus 6 dt plus, now the other one is 2 to 3, the absolute value again 2 squared plus t minus 6 dt. Now the thing is that if it's a negative function, absolute value means the negative of the function. So that means you multiply by the negative, because at that point it's negative, function is negative. So you multiply by the negative dt, plus here the function is positive, so we just rewrite no multiply by negative. Okay, good. Now we can integrate. So we can multiply by the negative sign and integrate. You get negative t3 over 3, negative t squared over 2, negative positive, so 6t. That's what you get. You can evaluate from 2 to 1, plus here it is t3 over 3, t squared over 2 minus 6 t, and then you can evaluate 3 and 2. So what you can do is just plug in the values. So if you plug in the values, what do you get? You're gonna get negative 1/3, negative 2 plus 12 from the first one, minus negative 1/3, negative 1/2 plus 6. From the second integral, you're gonna get 9 plus 9/2 minus 18, and then minus 1/3, 2 minus 12. If you simplify, you're gonna get 5. So this is a distance, so it is meters. So that's the answer for this problem. Okay, so you can see it's 5 meters because it's gonna go a long way, because as we discussed before, what happened is gonna go this way and then turn and come back. So you can see it's travel a lot. Okay, so there's a very short displacement, but we have a larger distance. Okay, that's about that. So I'm gonna give you a few problems for you to try. So these are for for practice. So let's do exercise, evaluate. So this is 3, so it's a 3a. So why don't you try square root t squared plus 3t plus 2 dt, and b, so it's a 3b. How about sine 2x over cosine x dx, and c, we can do ex plus 1 over x plus 3x dx, and d, you can do secant t plus tan t dt, and then e, how about x 4/5 root dx, and f, sin x plus sin x, hyperbolic sin x dx. Okay, so you can try these problems, and so for the word problem, you can try this one. So I'm going to call this is 4g. So you can try a particle has, so in short, okay, has the velocity function let's say vt equal t squared minus t minus 2 meters per second. Part A, find the displacement in the time interval 1 to 3, and then same, find the total distance traveled in the same time interval 1 to 3. Okay, so it's very similar, so you can try those two problems. So that's about indefinite integrals. So next we're going to move on to one of the very important section, what we call the substitution method. So let's talk about that. Now let's talk about the what we call the substitution method. So substitution method is the inverse technique to the chain rule. So this is simply the chain rule. So if you remember the chain rule, and you can probably rewrite some of the integrals without much trouble. So what we normally do is, if u is equal gx, so that's what we normally call inside function. If u equal gx um, is differentiable, is differentiable, then what you can do is the integral. So if gx, that's what we call inside function, g prime x dx, this integral you can write using the new variable u. So it's a fu du. So using the new variable. So what happened? The second integral is easier to integrate. So compared to the original one, it's easier to integrate because you can see that it's a simple integral. The g prime function is gone. Because of chain rule. Because when you take the chain rule, what happens is you get the g prime x term, but that's gone under this method. So, and then what we normally call u gx, that's what we call the inside function. This is what we call the inside function. Okay, inside function. I mean, that's pretty much. So your goal is to pick gx in the right way. Once you pick the gx in the right way, and how to do that? Yeah, because you know that you need to have the derivative. So we're gonna pick gx so that you also see the derivative there. So if you see a derivative of a function, then gx has to be that function that you have the derivative here. So that's how you check whether you have the gx and g prime x. Once you see both, then you can pick the gx. Okay, that's that. And then the next one is how to calculate the definite integral. So what we're going to do for definite integral, this is for indefinite integrals. For definite integrals, so what we do for definite integrals, we can do it two different ways, but we only to discuss one method. What we normally do is, so this is for definite integrals. What we normally do is integrate. So integrate using the u sub, integrate using the substitution. Okay, use substitution, and what we can do, use new limits. It's very important. You're going to use the new limits because the reason is your new variable is u, so you have to use the limit of u. Okay, not the limit of the original one. So you have to be very careful with that, because if you use the limit of the original one, that means x or t, your answers are wrong, because once you turn it, you kind of transform the integral from one variable to the other variable. That means you have to use the new variable. It's very important. So that means you can write the integral like this now. So we let's say you have a to b f gx g prime x dx. So now you transform this integral into f, the u variable. So if you transform the u variable, what's going to happen? You need to calculate the new variable. How to calculate the new variable? We again use the same transformation. In this case, u equal gx. So that means this is simply going to be g. You substitute the a value, the bottom value, and you substitute the top value. So that's what's happened in this case. You substitute the top and bottom values. So yeah, so this is what we're gonna use for the definite integrals. Okay, so let's do a couple of examples, and you can see that it's very easy. It's not that difficult. Okay, only thing what you want to remember for the second one is you have to use the new limits. Okay, new limits, not the all limits. So let's do a couple of examples. Let's say evaluate. The first problem. Let's say we have 2x squared plus 1 square root dx. Okay, problem like that. So if you see a problem like that, what you can do, you check whether you have the derivative. So you see a function, that's the inside function. Yes, you also see the derivative of the inside function. which is 2x. So things are easy. So what we can do, we can start with that. So we're going to say u equal the inside function, in this case x squared plus 1. Now what we can do, take the derivative. Once we take the derivative of both sides, so it's a du over dx. You can see it is 2x on the other side. Now what we're going to do, we're going to multiply dx. So we can write this one as du equal to x dx. So that means we have everything we need. We have this, and we also have a relation between du and dx. Okay, now we can use these two to rewrite the problem. So what's going to happen now is x squared plus 1 is u, so that means it is u square root, that means u 1/2. And then you can see that we have 2x dx. So you can see you have 2x dx, 2x and dx. So you can see you combine these two, 2x dx is simply equals to du. So that means you can replace 2x dx by du now. Okay, du. That's the 2x dx part. Now what happened? It is a new variable. New variable is u. You integrate with respect to that variable. So if you integrate with respect to the u variable, it is simply u. You add 1 divided by that same one, and then plus c. Now what you can do, you need to put that variable back. So that means your final answer gonna be, so you can write this as 2/3. So u equal that, so that means x squared plus 1 to the 3/2 plus c. So that's the final answer. So it's a very simple problem. Okay, very simple problem. You want to figure out u. Okay, so let's do another one. So we can do a couple of examples. This is one of the very important technique in integral calculus. So let's say x cubed sine x to the 4th power plus 2 dx. Again, you can see the inside function, that's inside, and then derivative is 4x cubed. 4 is a number, so we don't worry about those numbers much. So what you need to worry about is the function. So the 4x cubed, yes, x cubed is there. 4 you can manipulate, you can multiply and divide. So so what we can do, so let's start with the substitution. So substitution u equal the inside function x4 plus 2, and then take the derivative. Once you take the derivative, you get 4x cubed dx. You write like that, dx. Okay, so you can avoid that extra step. Okay, so so we have the two. So we have the substitution, and we also have the derivative differential part. So now let's go there. So you can see that the 4 is missing. You see, this 4 is missing. Since it is missing, what we can do, we're gonna kind of arrange the problem. So what we can do, we're gonna multiply and divide by 4. So we can write outside 4, we can write inside 4, and then we write the rest. So it is sine x to the 4th power plus 2 dx. Now you can see there is a 1/4. This is sine x squared plus 4 is u, so it's a sine u. And then what happen is, you can see x cube dx. This part is simply du. So we're gonna put du for that. Okay, this whole thing 4x cube dx is simply equals to du. Okay, now you can see in the under new variable, it's a very simple problem. So it is simply negative 1/4 cosine u. That's what we know. Sine u, integral of sine means cosine u plus c. And then you also the u back, so it is cos u means x to the 4th power plus 2 plus c. So you can see it's very simple, very simple. So let's do a few more examples because this is like one of the very important techniques. So c, how about this one? 2x minus 1 square root dx, because this is very useful also later in the integration by parts. So that's why this is so we can do this in two different ways actually. So what's the inside function? Obvious inside function would be u equal to x minus 1. That's the inside function. So take the derivatives, du. This is 2 dx. Again, 2 is missing. So what we can do is we can multiply and divide by 2, and then you can rewrite this one as 2x minus 1 to the half power dx, and then so it is 1/2. This is u, so u to the 1/2, and then 2 dx equals du. Okay, now we're going to integrate under the new variable. Our new variable is u, so it is u to the 3/2 over 3/2, and then you can see that these two get cancelled, um, and plus c, so that means 1/3 u 3/2 plus c. So let's put u back. So u is 2x minus 1 to the 3/2 plus c. So this is one way to do this problem. And also what you can do is you can also pick the whole thing as u. So I'm going to call c dash. So let's say we have 2x minus 1 square root dx. So the other way is I'm going to pick the whole thing as u. So u equal 2x minus 1 whole thing. So we can also do that. But if you do that, what we can do is we can square these both sides. Okay, so this is the other way to do it. Yeah, so we're going to put the whole thing. It's not obvious, but that's so we're going to square. So the u squared equal 2x minus 1. Now we take the derivative. Once you take the derivative, because of the chain rule, on this side you get 2u du over dx equal to, as before, when you multiply, actually you can cancel 2. Let's cancel 2 and multiply, so you're going to get u du equal dx. So it's slightly different this time, but that's okay. So what happened now is you don't need any rearrangements. So 2x dx square would become u, but dx is now u du. That's what you get. So that means it is u squared du. Where is it integrate? So it is 1/3 u third plus c. That means it is 1/3. U is 2x minus 1 square root. So that means 2x minus 1 square root to the cube power. So 3/2 plus c. So you can see it's the same answer. You get the same answer, but it's a slightly different approach. Okay. So let's do more. So the next one, D. How about this problem? X 1 minus 9 x squared square root, something like that, dx. So also in this problem also it is obvious what is the u in this case. So u is the inside function, u equal 1 minus 9 x squared, because you can see the derivative. Derivative is x, okay, actually negative 18x, but x is the one, so that's there. So we can take the derivative. Once you take the derivative, you get du equal negative 18x dx. You can see x dx is there, so negative 18 is not there, so we're gonna manipulate that. So that means you're gonna negative, so you can divide, multiply and divide by negative 18. Okay, so that's what we do. Negative 18, but it's kind of easy way to do it. Negative 18 x is there, and we're going to bring it to the top. So 9x squared negative 1/2 dx. You can write it like that. So negative 1 over 18. So this is u. So u to the negative 1/2, and negative 18x dx. Negative 18x dx is simply du. The whole thing is du. Okay, so it's clear. So negative 18x dx is du. Okay, now we can integrate with the new variable as before. So it is negative 1 over 18, and this is u. You add 1 divided by the same number plus c. You can see there's some nice simplification. This is 2 and 18, so you get 9. So and then so that means negative 1 over 9. U is that, so it's 1 minus 9x squared square root plus c. So that's what you get. Okay, good. So how about this one? Uh, e to the x plus 1 square root over x plus 1 square root dx. Again, if you think about, you can see when you take this derivative of square root x, it is 1 over square root x, 1 over 2 square root x. 1 over 2 you can manage. So, but the function x plus 1 square root is in the denominator, so that means that's the right choice. Normally, when you have exponential function, we always pick this part as u, complete the whole thing as u. So that's one thing you have to remember. So it is u equal whatever the power of the exponential function, pick the whole thing. Now take the derivative, we take the derivative, this is 1/2 x plus 1 negative 1/2 dx, or if you rewrite this one, you can write this one as 2x plus 1 square root dx. So we don't want to worry about this part because that's already there. 2 is not there in denominator, so that means we can multiply and divide by that. That means we can do a rearrangement. So 2, we can rewrite x plus 1 square root over 2x plus 1 square root dx. So we do that. Now we have everything in the right order, okay, because this whole thing is du. So now if you rewrite using the new variable, so you're gonna get 2 e to the u, everything else is simply du. Good, we know how to integrate e to the u, so it is e to the u plus c. That means 2 e to the u means x plus 1 square root plus c. Okay, very simple, very simple. Okay, now let's do some from definite integrals. So let's do some definite integral problems. So nothing much, you only have a new variable, that's the only difference. Okay, so let's do definite integrals. Definite integrals. So nothing much, so let's do problems. So f, so let's do 1 to e ln x over x. It's a very common problem. Again, look at the inside function. So as before, because we need to check the function and the derivative. So if you pick the function as ln x, the derivative of ln x is 1 over x is there already. That means we're going to pick this one as the inside function. And if you pick something else, it's not going to work. Okay. So we're going to pick u equal ln x, and then you can see du is simply 1 over x dx. That's already there. So that means this one you can write. Okay, what else? When you have numbers, you need to calculate the new values. So when x equal 1, u equal ln 1, you plug in the value, ln 1 is 0. When x equal e, u equal, use the substitution, the exact same substitution for everything. The same substitution for du, use substitution for new values. Okay, ln, what's the value? E. Where's e coming from? That's that. Okay, you're going to calculate those two. Okay, so ln e is 1. So that means what happened now, the new limit is going to be 0 and 1. Ln x is u, dx of x is simply du. So that's what happened. Okay, because so you can see this part du 1 of x dx, that's exactly sitting there. Okay, that's du is 1 of x dx. Perfect. So it's very simple integral. So this is very easy to integrate. U squared over 2. This is a definite integral. We don't add plus c, so it's 1 0. So let's plug in. So if you plug in 1 0, you get 1/2 minus 0. So it's 1/2. Very simple integral. So let's do a few more problems, because this is like something very important in the future. So G. So how about this one? 1 to 2 dx over 3 minus 5x to the something like square. Okay, same argument. So we pick u as the inside function 3 minus 5x du equal negative 5 dx, x equal 1, u, let's plug in x equal 1, u equal negative 2, x equal 2, u equal negative 7. Okay, those are the new values. So we calculate all of them at the same time, u, du, and the new values. Okay, there are 4 things to calculate. Now let's rewrite the new integral. 1 becomes negative 2, and then 2 becomes negative 7, and we need negative 5. So what we do, we multiply and divide. So actually let's do that before we do it. So we see the negative 5 we need, so negative 5 and then negative 5. We can bring this to the top, so 3 minus 5x negative 2 dx. Still the all limits because it's all variable. Okay, now let's change it. So it's negative 1/5. The new 1 becomes negative 2, or 2 becomes negative 7, negative 5 dx. So 3 minus 5x is u, so the u to the negative 2, negative 5 dx is du. Perfect. So this is equals to negative 1/5 u negative 1 over negative 1, and then this is negative 7 negative 2. So negative 1/5. So let's plug in the values. So when you plug in the values, so this is 1 over u with a negative sign, so it becomes 1 over 7, and then minus 1/2. Okay, so minus, yeah, it's become minus, become plus. Yeah, so this is minus, so become plus 1/2, and if you simplify, you get 114. So to get. Okay, so you can see it's not that difficult. Only thing that we need to do is we need to calculate the new limits. Okay, this is where we did that. So we always need to calculate the new limits. It's always a good idea to finish the integral with the new limits rather than going back. Okay, you can go back because you can substitute for u here, u equal ln x, and then use the all limits, but that's like wasting time. So because we just need to find the value somehow, the fastest way to do is use the new limits. Okay, so this is how you find a definite integrals. There's nothing new. You have to always calculate the new limits. New limits, that's the only extra step compared to the uh, indefinite integrals. You have to calculate the new limits. So new limits always goes in the integral. Okay, and then we also talk about what we call the four formula trick. So I'm going to recall that, the four formula trick. Uh, four formula trick. And also you can find the link in the description if you forgot that, with more examples there. So this is the four formula trick. Four formula trick. So we use this throughout the course. So sometimes we call FF trick. Okay, FF, four formula trick. So what are the four formulas? The first one is general power rule, Fx. If you have nth power, f prime x dx, integral. So what you can do is, if you see the function and its derivative, you can simply treat this function as x. So if you treat this as x, your answer would be fx to the n plus 1 divided by n plus 1 plus c. So this is what we call the general power rule. This is when n not equal to -1. That's the first one. The second one is, if you have e fx and then f prime x, so what happened, you can simply treat this one as x, so that means answer is e to the fx plus c. You can see it makes the calculation much simpler and faster. So this is very useful when you try to take differential equation classes, because we use that a lot there. And then we have fx f prime x dx. So this is simply natural log, okay, because when you have the derivative on top, this is natural. So ln fx dx, ln fx, absolutely, plus c. So that is the n equal -1 case. So this is the n equal -1 case. And then number 4 is also useful. This is very useful in integration by parts problems to the nth power, because n normally be square root, like n equal 1/2. So what's gonna happen is, think about, because if you have the derivative there, this is simply the case 1 actually. This is a special case of case 1. Fx is ax plus 1. So what's the derivative? A. So that means you need to multiply and divide by a. That means the answer is gonna be ax plus b to the n plus 1. In the bottom, you should have a. You also should have n plus 1 plus c. Okay, so this is again n not equal to -1, and a not equal to negative is obvious, because otherwise it's just a constant. Okay, those are the what we call the 4 formulas. Okay, 4 formulas. Let's try to do like a couple of examples from that, and you can see you can get the answer very quickly. So this is what we call the 4 formula trick, or FF trick. Okay, so you can directly use this one, but use it properly. You think remember, like every time you see the derivative, that's how you remember. See the derivative, you always see the derivative. Okay, good. Here the derivative is constant, that's why you don't see it. Okay, good. Let's try to use this and solve like some examples. Uh, so h according to our list. So let's do tan x. Let's do tan x. So if you want to do tan x, this is also in the 22 table. But if you don't know, then let's write tan using sine cosine. So sine x over cosine x, and you can see that the derivative of the bottom function is negative sine x. So what we're gonna do is we can put the negative out, negative in. Okay. Now you can see this is the formula number 3. So if you use the formula number 3, the FF trick, you can see this is simply negative ln the bottom function. Directly confirm. This is actually substitution method, but you can avoid that. Okay, this is substitution method, but you can get the answer much faster. Plus c. Now what we can do, we can bring the negative sign inside. If you bring the negative sign inside, what happened? We know that in the log is gonna make the term inside upside down. So that means 1 of cosine means secant. So it is a ln secant x plus c. That's actually a formula. Okay? This is one of the formula in the 2 and 2 table list. So similarly, we can do the cotangent. So let's do cotangent x. So the same thing, cotangent means cosine x over sine x. But the interesting part here is that's already the derivative. So that means this is simply ln sine x. You don't want to do any other simplifications, any other modifications. It's much faster. How about this one? So let's do a exponential function. Tan x secant squared x dx with some limits. Let's put 0 and pi over 4. How about that? And you can see this is fx function, this is its derivative. So according to the 4 formula trick number 2, so for the formula number 2, you can see this is simply e tan x, because that's the derivative, and then evaluate at pi over 4 and 0. It's very simple. So it is e tan pi over 4 minus e tan 0. Tan pi over 4 is 1. So this is equals to 1. This is equals to 0. So that means you're gonna get e to the 1 minus e to the 0, which is e minus 1. Okay, e minus 1. That's what you get. Good. So let's do maybe 2 more examples. The next one is k So how about this one? E to the 2 1 over x ln x square root x dx, like that. Again, you can see the function here is ln x square root. Derivative of the inside function is 1 over x. That's there. So that means you can simply write the answer right here. So this is square root. So that means ln, you add 1. That means it's going to be 1/2, positive 1/2, divided by that same one. That's it. And then 2 and e. So very simple. Okay, simply coming from the for formula number 1, general power rule. Good. So let's plug in the values. So if you plug in the values, you're gonna get, so 1/2 divided by 1/2 is 2. Let's plug in the values. So it is ln 2 square root minus ln e square root. Ln e is 1. Square 1 is 1. So that means your answer going to be 2 ln 2 square root minus 2. That's the decay. And then L, so let's do this one. How about this? 3x minus 2 over 3x squared minus 4x plus 2 dx. It looks complicated, but it's not. What is the inside function? 3x squared minus 4x. What's the derivative? 6x minus 4. So you can see, you can get that by multiplying and dividing by 2. So we can divide outside by 2, we can multiply inside by 2. So it is 3x squared minus 4x plus 2 square root dx. And you can see now we can use the general power rule again, number 1, because the this is the square root power, and the derivative is right here. 6x minus 4 is the derivative of that. So you can simply treat this one as x. So if it's not clear, we can rewrite this one if you want, but this step is not necessary. You can bring this to the top. So 3x squared minus 4x plus 2 negative 1/2 power d. We can write it like that. Then you can see it's very simple, because this is the inside function and that's the derivative. So we can use general power rule number 1. So simply treat this one as x, so it is 1/2. If you treat this one as x, 3x squared minus 4x plus 2, the positive 1/2 divided by the positive 1 plus c. 1/2 get cancelled. So your final answer would be 3x squared minus 4x plus 2 square root plus c. Very simple. Okay? Very simple. So that's about that. And there's also like a small one that we normally discuss in this one, what we call the even and odd functions. So what can happen if you have an even function or odd function? So let's talk about that before we finish this section. So even and odd functions. So what's the even function? So f is even function. F is even if the negative value is exactly equal as the positive value. So that means in the graph the function looks even. That's why we call it even function. Oh, that's not. So it looks even. Okay, so like that, go like that. So like it's an even function. So the idea is the value at the negative x is exactly equal to the value at the positive x. That's why it's called even function. You can cut in the middle. Two sides are the same. And then if it's odd, F is odd if the negative value is the negative of the positive value. So in this case, what happened, if you look at the graph, the function goes like that. So the negative value is equal to the negative of the positive value. You can see they jump from positive to negative. That's even function. Now what happened, then there's a theorem, a result, which says that if f is even, if f is even, that means negative a to a fx dx, if this is even, what happened, it is twice the half of the value. So twice one side from 0 to a fx dx. And why we need this one? This can make some of the calculation much simpler because you're gonna plug in 0 for one value, so that's much faster to calculate. Okay, that's one of the benefit of that. And similarly, if f is odd, what happened, negative a to a, because since one is positive one is negative, because you can see you can write this on negative a to 0 fx dx plus 0 to a fx dx, and you can see they are the same but opposite sign, so they cancel each other, so you get 0. Okay, so it becomes 0 if the function is odd. So let's try to do two problems from this one, just to remember the idea. So you're going to say evaluate. The first one, actually let's example, evaluate, and then let's say the first one. First one is, let's say, negative 3 to 3 x squared minus 4 dx. So this is 2 times. So you can see this function is an even function. Why? All the powers are even. All the x to the 0. 0 means even number. So this is an even function. It's an even function because all the powers are even. So that means this is, you're going to get the half of the integral and double it. So you're going to get 0 to 3. X squared minus 4 dx. This is very easy to integrate. So this is x3 over 3 minus 4x. 3 is 0. So it's 2 times, you plug in 3, so you get 9, minus you plug in 3, 12, minus 0. That's the benefit, 0, because it's gone. Okay. So you get negative 6. You can see it's very simple. And the next one is, let's say, negative 1 to 1 tan inverse x divided by 1 plus x squared plus x to the 4th dx. Okay, what do you know about those two functions? The bottom function is clear. These are all are even powers, so it's an even function. Okay, all are even powers, it's an even function, because you can see that when you plug in negative x, you get the exact same one. What about the top one, tan inverse x? It's an even function, odd function. We know that tan is odd function, so the inverse is also odd function. So this is a odd function. What's the graph of tan inverse x? Remember? What's the graph of tan inverse x? So it's gonna go between the two values, negative pi by 2 and positive pi by 2. So that's the tan inverse x graph. It's gonna go stuck with pi over 2 and negative pi over 2. Now you can see it's an odd function. It's an odd function. So when you have odd function, even function, when you divide or multiply, the answer is going to be odd. Because the even one does not change anything, but the odd one change the sign. So that means finally it's going to be an odd function. The whole thing is odd function. So that means it's odd function. So it's odd function. So that means 0. You don't have to do anything. So you can see the benefits. You need to figure out that. So how you figure out this kind of question? You can see a complicated problem. You probably try to guess that. Okay, so what are the things that we remember? If you have odd and a odd means even, because both can change the sign, so finally it's a positive sign. If you have even is even. If you have odd and a even, multiply or divide, it doesn't matter, both. So it is a odd function. Okay, they have if they are different, it is odd. That's how I remember. Whether you multiply or divide, it doesn't matter. Whether multiply or divide. Okay. Good. So that's about that. So I'm going to give you some practice problems that you can try, and you can see the answer is in the description. So you can try these problems. So these are the exercises. So exercise. So this is 4a. So let's go with cosine square root t divided by square root t dt. B dx over 4x plus 7. C dx over 4x plus 7 square root, and D sine t 1 plus cosine t square root dt, then E cosine theta 1 minus sine theta. I think we did one of these problems in the quiz. Cosine theta 1 minus sine theta. So I'll do F. Let's do cosine 7 theta sine theta d theta. G e to the u 1 minus e to the u whole thing squared du. Let's do H sine 1 of x over x squared dx. I ln x whole thing squared over x dx. It's obvious, I think. And j sine x sine cosine x dx. And then k 1 over x ln x. We did a very similar one. KL how about e to the tan inverse x over 1 plus x squared. The last one, let's do this one. T e to the tan t divided by we can say 5 minus t squared plus t to the 6 dt. Okay, this gonna go from -1 to 1. So actually I'm gonna put another limit here. So 1 to e. This is interesting if you put 1 to e there. Okay, so let's do that with 1 to e. Good. So you can try these problems and you can see the answers in the description. So next we're going to talk about applications of integrals.